Hello everyone and welcome in this presentation. Do you think that doing security correctly in an embedded IoT on edge product is complicated? You may say that it is. I would say that it depends. It depends if you are starting from scratch using best practices, or you are entering in an existing project that was started without any security best practices whatsoever. And then you need to fix everything together. And even in this situation, it's not that complex as it could be when you go over fixing those problems step by step. Today, I'm going to share with you my 5 favorite steps in improving IoT security. Five steps that will help you to improve every single project you're working. But first, who am I? My name is Marta. I have been working in security. I've been working in the security for the last 15 years with a PhD, and during my career, I've been working for different types of companies and different projects between chip vendors and device makers. It means that I have seen different realizations, different levels of projects, and different needs of configurations. I'm currently a technical program manager for the Eclipse Foundation, and I'm helping the Eclipse Foundation improving security in its projects. Now, the experiences I'm sharing with you today come from various systems I have been working on in the past. Mostly Linux-based systems, but also RTOSes like Zephyr, FreeRTOS, and proprietary ones, and the recent experience in distribution making in the Eclipse on Nero project. When you will be looking online to find out more about challenges in IoT security, what you are going to see is hundreds and hundreds of horror stories of projects and products that have been used for malicious purposes. There are different ways of describing those, but here is the list of the most common ones that we can find out. We can find IoT products used in a botnet. What is a botnet? A set of machines or devices, it may be a small embedded one, used by malicious person to launch attacks against some other infrastructure. Typically, the frequent case is have them used as a set of devices doing a distributed denial of service attack. So flooding a device with, or a network, or any other victim with traffic. But there are different ones also. It may be used to get information from the device, to launch otherwise malware against other networks. So all of possible uses that could happen if the device is badly configured and if it's badly secured. Then we have vulnerabilities in firmware. And here by firmware, I understand the software running on the device, but also firmware in certain subsystems of the device. Quite frequently, you have separate firmware in your Wi-Fi chip. There may be a separate firmware in the Ethernet chip. There may be separate firmware in your graphics chip. There may be vulnerabilities in the firmware in the main code, but also in different other codes. The vulnerabilities of firmware are quite frequent, and we also have news stories related to them. IoT devices those days use networks, of course, multiple networks. We have not only at Ethernet, we have Wi-Fi, we have specialized networks. The previous presentation had an example of a multi-device, a multi-network setup used in a typical IoT product. That is what we need to deal with. Those networks have different levels of protection. Some protocols do not have any encryption or authentication whatsoever. Some of them have it, but it may be disabled or not, or activated only in certain cases. All protocols, all networks need to be checked out because they may be a serious problem related to those networks. Then we have data privacy concerns, not only about the device saving location or personal information about the person, passwords, and other items like that. We have examples of products like embedded cameras, badly secured, that allow everyone to connect to the device and watch or redirect the video stream to any place they want to. Definitely something you do not want to encounter in your product. And then finally, we have quite often missing encryption. Missing encryption on the device for the data or for the traffic being sent or received by the device. That is a lot. That is a lot, and if we were trying to fix each of them separately, there's already a lot of work. But we can use another technique. We can look deeper into why is it happening first. This is happening in a world where developers have requests for more and more features all the time. There is a limited time to market. The device needs to go out as soon as possible. And on the other hand, the support of the devices already deployed is often limited, or there's little effort on that side. We have multiple networks protocols in more and more complex configurations that developers have to deal with. And we need nice user interfaces. What it brings is a lot of work for developers. If you want to secure the devices at the same time, it is a complex thing to do. My proposal: a security principle of defense in depth. What it means? It means that we use multiple security measures at the same time. We use them at the same time so that if we have one layer that has a hole and that hole could be used by an attacker. There's another layer protecting the device. Imagine old castles that had the first wall, then there was a second wall that was a castle, and there were different levels of protection. We do the same thing, but to protect our device. Coming from castles to IoT examples. An example of defense in depth for an IoT product would be train developers on secure coding, or in general on best coding practices. Add mandatory code review, if possible, by 2 different persons. Add tests for new features and for existing features. We secure the default configurations, including passwords and all other elements. Run applications on the devices with lowest permissions possible that we can on our system. Enable hardware protection, like the MPU and MMU. On the Linux-based systems, we have MMU. Always on smaller architectures, and resources, the MPU or MMU, if it's there, it may not be enabled by default. On the bigger platforms, we may have also other hardware protection mechanisms. We may have crypto accelerators and many other things that we can use. And then finally, secure update of the product. As you can see, some of those techniques are not really security measures. Test is not something that most of people will consider a security measure, but it actually is. All those measures are working together, allowing the product to be protected for most places, but at least 2 different measures. Developers who are well trained will do less bugs. Code review is going to remove even more of them. Tests won't let regressions in, and so on and so on. All of those techniques will work together. Now, I'm going to present you my 5 preferred techniques, 5 of those building blocks for the defense in depth. Each of them I will describe with the same structure. There will be what to do, why, what are the gains, not necessarily only in the security field, there may be other gains, and then next steps if you are interested in that method and want to get further. So let's get started. My first and favorite technique is removing unneeded dependencies. What does it mean in practice? Review your package list or configuration options. Package list will be in a Linux-based system, configuration options in smaller systems. The same reason to look for features you do not need. For every feature, have a look and ask yourself questions like, do you know which visible feature requires this one? Or maybe was it there by default and we never decided to change it or even think about why it should be changed? And then finally, what breaks if you remove it? If nothing breaks, it may be that it's just something that you do not need. What we can look into even in more details are debug options. Those quite often open access to code and to data that we do not want to allow access. And quite frequently, we do not need debug features on a production device whatsoever. So, debug options that can be forgotten are, for example, debug tweaks when you are using the IoT project's configuration. It's an option adding some features that are useful during the development time, but it should never be enabled on a production device. It happens that people just forget about this option and leave it on. And then the other suggestion, look if the debugger is there or a compiler is in your production image. Usually it shouldn't be. You do not need debuggers and compilers on production images. Now, why do we do that? We are making the attack surface smaller. Attack surface is all those places where the attacker could access your device. The best way to have code without bugs is to make sure that this code is not there. Another reason to remove unneeded options is that if you do not use them, you likely do not test them. And not tested code means that bugs are more likely to be added and to stay. Removing unneeded code then allows us to remove the code that will likely have more bugs than average. So it will be beneficial for the overall quality also. Now, what is the gain of removing a needed feature? That is pretty simple. You have a smaller image in terms of code, in terms of flash and memory usage. So it should be beneficial for the product itself. If you are more interested, if you want to know more about your device, if you want to compare what you have in one device to what you have in another device, you may have a look at software bill of materials, a field that is very active right now. You can have a look how to generate and how to use SBOMs in your device. That could answer quite many questions about what you actually have in the device. Let's move to the second technique. The second technique will be restricting remote access. There are quite many things you can do to restrict that access. If your device has SSH access, remove root login. In OpenSSH, that's permit root login set to no in the configuration file. But in general, remove all login for all users that you do not need. I can always sometimes see even telnet enabled in some devices. So if you have that, remove. Instead of SSH, you may consider using hardened special purpose consoles if you want to have a console-based access, and for example, you don't have a web interface. So then you can restrict the commands that are being run. Could be a better option than just SSH access. Allowing a login from the external networks, that is something that we should restrict and allow, especially the web administration, only from the internal network. That doesn't protect against everything, but it already remove some kinds of attackers. If you are using a web-based login, for example, for a web-based administration, then use HTTPS even if it's in local network. Especially if you are passing passwords through the connection, definitely use HTTPS even if it's in a local network. And then last but not least, change the default passwords. When I started doing embedded IoT 15 plus years ago, it was pretty common to have devices with root login with password as password or login with admin. That has changed, but still there are some devices you can buy that have that configuration. You should definitely use different passwords for every single device if possible. Why do we want to restrict remote access? The first thing to know is that the scans for weak passwords are automated and they are running daily. If your device is connected to the internet, it's going to get scans for weak passwords every single day. So it's not going to last very long if it has a very simple to guess password. Breaking access to the device may have important impact. An attacker could be able to run malware on device, flash, or wipe it completely. So it is an important risk for the device and for the user of your device. Now, if you restrict the access, what are you going to gain? You are going to gain the removal of big part of the automated attacks. As said, SSH scans happen all the time. And you are diminishing the risk of being a source of news, let's say, of hacked devices. If you are more interested in those types of techniques, in making access control better, consider also separating and or sandboxing your applications. Restrict a list of available ports. It may be that certain ports are needed for internal operation of the device, but they do not need to be accessed by anyone outside the device, so you can block them either in the code or through a firewall to allow any network access to those ports. And then you may consider moving certain important services that you want to keep for some reason to non-standard ports. The typical thing is to move SSH to a different port. This is not really a security measure, it's a workaround, but it can remove some automatic scanning. Now, my third technique would be to use tested crypto libraries only. Crypto libraries are everywhere. In every product, you have at least one of them. And you may look, while implementing the first technique, you may want to figure out how many you exactly have. My suggestion is to use only well-tested libraries. Never implement your own protocols, and by your own protocol, I do not mean encryption only, but I also mean authentication, key generation, or hash. Use algorithms and protocols that are well tested. And then follow best practices in algorithm choice. We are in 20 23 right now, and we shouldn't be running DES, we shouldn't be running MD5, and we shouldn't be running SHA-1. If you have those, consider removing them when possible. Why do I suggest you to use only well-tested crypto libraries? Because good crypto is hard to do. Crypto can be easily implemented incorrectly, and not only incorrectly at the functional level, but there are also attacks that are using other features like the time it takes to calculate with different keys or with different bit values of the key to recover keys from the implementation. Some of them are practically usable on an IoT system. Well-tested crypto libraries have the algorithms that are usually implemented in a way that protects against those attacks, and you can ask authors about what level of protection they have. That will be way more practical than trying to implement all those mitigations on your own. Now, what do you gain from a well-tested crypto library? Usually you get better performance and less fingerprint. So it's a good reason to do so. Sometimes you may have a little bigger footprint than you would do when implementing it manually because of the mitigations for different kinds of attacks. Still better to use well-tested library. If you are a heavy user of crypto algorithms, have a look at hardware crypto that may not be a good solution for your case. Run test suites of your crypto libraries to make sure they're running correctly, and verify your random number generator. Generating random numbers is very important for good cryptography because good random numbers are, for example, needed to generate keys, and if you have bad random numbers, your keys are very easy to predict. What remove the whole protection you have from the good crypto. Very important, verify random number generators. And if you are more interested into learning why doing good crypto is complicated, I'm providing you links, historical links, to contests that were run to select the IS algorithm and the SHA-3 algorithm. You can find all of the candidates that were evaluated. Quite many of them were broken during the process. You can learn how and why, and that could give you more insight about why even people who submitted their algorithms to the contest did mistakes in them. So probably even more mistakes for someone doing the crypto algorithms just for the first time. Now, let's go to a completely different area, to logging and audit. I suggest you to have logging and audit in your system. Especially add persistent logging, ideally in a dedicated space. And examples of events that could be logged in that place are critical errors like lack of a space on a device, crashes of applications, which applications are being run as a root user and at what time, and changes to critical files. When logging, make sure you are adhering to GDPR and you are taking users' privacy into account. typically avoid logging locations or passwords for the user, typically for security reasons and for diagnostics. You won't need that. So decide carefully what you need to log and what makes sense and what doesn't. Why do we want to have logging and audit? If an attack, or maybe when an attack happens on a device, it allows us to better diagnose what happened or what is happening in the real time. It also helps us to diagnose if a device was compromised or not. In addition to that, we gain a device that is easier to debug for not only security, but also for functional problems. Good logging is something that is frequently overlooked, and then it could be complicated to figure out what is happening on a device that is not working as we expected to. If you're interested, review the default configuration if you're running on Linux of audit, and consider doing an append only log, a log that you can only add to, but you cannot write to remove existing content. So let's move to the fifth subject, that is the last one, because it could be more complicated to put in place than the other ones. Updates. Having an update in a device is a security measure. And also providing security updates for your device is an important feature to improve security of the device. Why is it so? Because there will be issues in the software that you have included into your device. Some of them may be critical. If you have no other way to mitigate the issue, for example, you cannot disable a configuration option to remove the code that has an issue, the only way you can mitigate is to do an update of the device. If you cannot do an update, you are stuck and you use this with you with a device with a critical flow in the field. That could be really problematic. The additional gain is that your device can evolve. Imagine linking device updates with the first principle of removing unneeded software. We may be tempted to add features that we do not really need right now because we may have a feature to enable it later. If you can update your device, you can add all that code later. You don't have to ship it just at the beginning. If you do not have updates yet on your device and you want to look more into update systems, there are a lot of resources online on that. Have a look at signed and verified updates. Just having an update that isn't signed or isn't verified is not enough. A signed update can be verified that it comes from the vendor and it's the file that it was expected to land on the device and not some kind of a malware. And then your device will be verifying that the update is correct. Either that is correct because it comes from the right source or just it was downloaded correctly. And then quite many devices use a rollback system with a kind of A/B update. When you have two copies of the software and you update only one of them, then try if everything works correctly and it boots correctly before committing to that new version. So we have covered quite many subjects today. The suggestions I give you are remove unneeded dependencies because they may be bringing issues and they take space that you may need otherwise. Restrict remote access to interfaces and to services that you really, really need. Use tested crypto libraries to avoid incorrect or vulnerable implementations. Add logging and audit to be able to diagnose the device. And perform updates of your device so that you can fix issues that show up over time. And before we wrap up, let's come back to defense in depth. You have seen that the techniques that I have shown you today, they are not all and totally only security related. They are functional. And that is the principle of defense in depth. We work with multiple layers, adding features and adding protections at the same time. We have started talking about testing, and I would like to mention yet again that better quality of code usually means better security. A code that has less bugs, less generic bugs, will have also less security bugs. All initiatives to improve general quality usually will have impact on the security also. If you have many things to improve in your project, remember that even small steps count. Even small changes can provide improvements, and even small improvements can protect some users. So they are still worth implementing even if they are not fixing all the issues that you may see. Step by step, one by one. And this will be the time for the questions that you have for today.